and welcome to today's webinar on enterprise data storage, lakes, warehouses, and more, a crash course. I'm Megan Winnery, Senior Demand Gen Manager at Telium, and I'll be your moderator. Before we get started, I'd like to go over a few housekeeping items. This webinar will last approximately 30 minutes and will be recorded. The slides and the recording of the presentation will be made available at the end of the session. You'll find some related resources in the attachment section that you can view during or after the webinar, so check them out. And we want to hear your questions, so please use the Ask a Question feature to submit them. And for any that we aren't able to answer live, we'll follow up with you after. And you'll notice that we have a social hashtag for today's webinar in the lower right-hand corner of our deck, hashtag Telium Data Storage Webinar. And we encourage you to retweet, like, and share as we live tweet throughout the webinar. All right, and on to today's presenter. We have Ted Svikas, who is the Director of Telium's Solutions Consultants Organization in North America and Latin America, which is a team that works with Telium's customers to build strategic solutions and that work with the Universal Data Hub and automate the data supply chain. He has over 17 years of experience with a number of leading organizations within digital marketing, social platforms, SaaS-based telephony and messaging firms, ITSM portfolios, and automated quality assurance technologies. Prior to joining Telium, Ted worked in a number of senior-level advisory positions for CA and HP, where his focus was centered on lean IT methodologies throughout financial, healthcare, manufacturing, and retail industries. All right, let's get started. Ted, over to you.
Thanks, Megan, and thank you all for joining the webinar. In this session, we'll be taking a look at two of the most popular types of enterprise data storage technologies, the first being enterprise data warehouses, or EDWs, and the second being data lakes. We'll talk about what they are and learn about why they have become so popular and the value they provide businesses that use them. We'll see how they're actually designed and used so that we can understand their specific importance in managing data and producing relevant business information. In the second part of the session, we'll take a look at the current day status quo and see how EDWs and lakes have evolved to coexist together. We'll understand the different pros and cons with each of them. More importantly, we'll look at the current challenges that both of these data storage platforms continue to face, and we'll tie it all together by suggesting a new solution to address those issues. All right, so let's start by taking a look at the EDW. Why do businesses need an EDW? Well, for starters, the EDW represents a centralized storage point, and this is an important architectural design. Without EDWs, data resides in siloed system databases, and accessing that data becomes a challenge for a number of reasons. By centralizing, access to this information is now more practical, and better processes can be formed for that purpose. The second reason is that the EDW is also relied upon for the information that produces insights, decisions, and reporting. That's the whole reason an EDW exists. During the last 10 years, most organizations have become data-driven to a large extent, and the EDW's role in supplying business intelligence tools has been strengthening for quite some time. Data in the EDW is broad and it's deep. For example, very rich historical and contextual information about suppliers and related supply chain information, transaction records, invoice records, service desk and help desk history, and customer data sets, amongst others. Hand in hand with the term EDW is the term ETL, which stands for extract, transform, and load. An EDW is given data via lengthy and sophisticated ETL processes run by a number of people and technologies in the organization. The steps taken to extract, transform, and load data follow a very strict process whose steps are designed by data professionals and are typically implemented using a variety of technologies. EDWs also act as a reliable and important tool set in the higher strategy of promoting data sharing enterprise-wide. Most organizations have this strategy at the top of their list, and the centralized nature of the EDW delivers accordingly. Next, the nature of the EDW's structured data set results in increased trust in the data, and therefore will directly improve data quality while mitigating reporting errors that would have otherwise taken place. One important characteristic of EDWs is their role in aggregating data about all topics for all departments and merging historical and current data sets together for those topics. Ultimately, EDWs stage data for viewing in the visualization tool of choice. This is important for analysis and decision-making because BI tools like Tableau or Power BI or Domo, etc., are all built to look deep into the past and build insights and trending analytics based on that evidence. So without an EDW to provide the BI tools with this rich set of data, these reports could never be built with the degree of agility and quality that we see today. So let's take a closer look at how EDWs are typically designed from both a product perspective and a process perspective. First off, from a product perspective, we can see the data flow in this diagram from left to right. Starting from the left, we see that EDWs receive data from specific approved data sources. Now, these source systems can be online transaction processing systems, OLTP, or they can be siloed databases from external technologies that contain some kind of organizational data that is important to centralize for a larger purpose. Now, you can see the blue ETL steps to the right of the source systems, and this indicates that all of the disparate data from these source systems go through the extract process at this point before being delivered to the EDW's staging area. This is where all the data now needs to be transformed to match the EDW's schema. These first two steps are planned on a schedule, and the goal is not to produce a rapid result. A key point to make here. Timeliness is less of a focus than accuracy. And that's why you hear about EDW data being highly structured, precisely planned on a schedule, and conforming to strict entry rules. These descriptions are more easily referred to with the term schema on write. A schema is simply a blueprint of how a data model looks like and the format that that data must be in order to be part of the model. So schema on write is a good way of explaining that data must conform to the blueprint the second it is written to the EDW itself. Now, this is where the transform part in the acronym ETL comes into play. Where data engineers transform this data, they are doing all the cleansing, formatting that is needed to have all of these source systems data conform to the warehouse schema. And when that happens, we move to the center of this diagram with the final step in the ETL, the load phase. Loading the data into the EDW follows even more strict deployment processes to ensure data integrity and for auditing and security purposes. But once inside, that data is finally activated for use by moving it via more ETL processes into a number of different databases called data marts. Data marts represent the information needs of all the different organizational business units who want a subset of that EDW's massive data set for a specific purpose. Data marts are easily plugged into the BI tool of choice to visualize the latest data set that these individual business units want to see. For example, the sales department in an enterprise would have had a data mart that shows all prospect data sets for lead management purposes, for example. And all of this data came from a half dozen different source systems. Instead of the sales department having to chase down the source systems owners, the EDW process has given them a nice way of getting all that data centralized and accessible into one convenient data mart. Now all the sales department has to do is hire a BI analyst to work with the data in question instead of wasting time and money doing all the heavy lifting getting that data for themselves. We'll leave off this slide by mentioning the 4 types of data that the EDW will be working with. Non-volatile data is simply data that is saved from persistent storage. We're talking about emails, log files, even data on CDs, and of course other databases, etc. Time-variant data is also something that is very popular in EDWs. These are the records of data that span a time horizon. All changes are logged and saved. A good example is a big record or a ledger of loan history and all the payments that are made. The warehouse will have all of that transactional logging within it. The third type of data is subject-oriented, and this is data pertaining to specific departments. So whether those source systems are tied simply to sales or R&D or product development, they will be arranged in the warehouse accordingly. And the last type of data is integrated data. This is pre-configured and cleansed data from multiple data sources, whether they be flat files, transaction records, other databases. This is where your professional engineers build and merge that together to form even new data or enrich data. To get a better understanding of how the operation of an EDW and the necessary support it requires, let's take a look at this same diagram, except this time with people and process drawn in. As you can see, each source system likely has a subject matter expert linked to it that will have an understanding of how to work with EDW personnel to begin the ETL process. Below the source systems, we see some icons with stop signs. This is indicating the process and time required to have these two groups of people work together in a secure, controlled manner. In effect, they're orchestrating their activities manually. In fact, as we follow the rest of the diagram along to the right-hand side, we can see that there are process expectations every single step of the way. Data engineers will work to ETL the data and be compliant with a rigid but very effective process to ultimately turn data into useful information. The main takeaway from this slide is that as we move from left to right, the cost and the time required to manage the data's journey certainly increases. And just as important, we see that going the other way, the risk of data becoming stale once it arrives to the business also increases, and that is because by the time BI tools start producing insights on this data, the source systems have likely spent days or even weeks collecting new, relevant, and related data. On that note, we all know that no technology is ever purchased until the benefits outweigh the costs, times, and risks associated. While certainly the EDW's benefit is tremendous, it is important to view the cost, time, and risk factors that are necessary to realize those benefits. First off, from a cost perspective, we've just heard that they're very expensive to purchase and manage and maintain. This is because of the technology involved with the setup, as well as the people implementing the processes. It's also very costly to design from both a time perspective and a substance perspective. The right professionals have to build the schema, and they have to be in collaboration with the business the whole time. Very costly to support as well. Many organizations spend upwards of $10 million plus to set up an enterprise data warehouse. Now, solely from a time perspective, it takes a long time to gain insights. The data through an enterprise data warehouse does not move through a real-time data supply chain. It arrives slowly, but assuredly towards the business. The data models require, therefore, a lot of long processes and many personnel to govern and orchestrate the data from their perspective every step of the way. And the last point to make, risk. The data warehouse has a high capability of causing errors in analysis whenever real-time requirements are in scope. In fact, many people will tell you it's almost impossible to gain a real-time insight by using a data warehouse because, once again, by the time data arrives at the endpoint of a data warehouse, the business, it's usually somewhat out of date to some extent and very difficult to activate and move across the organization in order to gain further insights. So now that we've seen the overview of the warehouses, let's explore the data lake in exactly the same way. Just like an EDW, a data lake is a centralized storage technology, but unlike an EDW, whose data is very structured and conforming to a schema, the data coming into a data lake is unstructured, and its value is not yet clear. This new approach to centralizing data is different, and it means that different source systems can now be part of the data flows. Since data does not follow a strict process when going into a data lake, the data sources only need to transmit to the lake without regard to format or size or compliance of any need. That is now dealt with later, as we'll see shortly. Once the data is in the lake, a variety of tools are used by experienced developers and data scientists to create insights and build useful information sets for a department or to address a technology requirement. Very similar to an EDW, except later on in the process. And also along these lines, lakes promote data sharing, but in this case, it's mostly through IT, and the business typically doesn't get involved at this stage in the game. And that is because in order to work with a data lake, skilled professionals with a good amount of technical knowledge are needed. A last point to make about a data lake is that one of the early points of enthusiasm about them were focused on costs. As companies struggled with the ever-increasing amount of big data that they needed to process, they realized that enterprise data warehouses had their limits. EDWs are costly to set up and operate, as we've just discussed, and that's just considering some traditional source systems. What about the data being sourced from the billions of new devices coming in on the market every year in the mobile space, Internet of Things market, audio, video, and media content from over-the-top devices like virtual voice assistants and streaming set-top boxes? EDW infrastructure would be prohibitively expensive to purchase as the cost of storage would skyrocket trying to collect and ETL all of that data. But as we'll see with data lakes, the problem was largely mitigated through data lake architecture called Hadoop, which essentially provided a very scalable, efficient way of distributing all of that data across clusters of computers instead of one massive data warehouse. Hadoop's inherent approach to separating the compute steps from the storage destinations in the cloud allows businesses to purchase data lakes using Hadoop architectures, which give the lake the ability to scale up from a handful of servers to hundreds or even thousands of servers dynamically and storage as required and on demand. The goal of a data lake is to deliver information to business organizations, but also to other systems like machine learning tools, for example, for further processing. On the left side of this diagram, we see that as opposed to an EDW, which uses well-known source systems from the enterprise to collect data from, a data lake is wide open to any system or device, regardless of where those devices or systems may lie. It's a big assortment of devices that are producing big data. They can be social, video, email, spreadsheet data, whatever the case may be, and that data flows to the right where it ingests into the lake with predetermined ingestion techniques already configured by data engineers and the APIs associated. So in this case, we have a single shared location for all our data, just like EDWs, but it's unstructured data, which means it needs to be worked with by knowledgeable engineers and scientists in order to be made useful. This is why we call a data lake's approach by the opposite term, schema on read instead of schema on write. It's because the data in a lake does not have to conform to a model prior to entering the lake, but instead it will conform to a data model after it is read by the engineers and ultimately formed into a usable set of information. So the schema in this case is enforced after entry into the centralized system, in contrast to the EDW where the schema is enforced prior to entry. To make data useful requires similar processes as with ETL steps we just saw with the EDW. In the case of data lakes, the process is to blend multiple sets of data together where the context of the resultant data set makes sense. For example, a company has a mobile app that it provides customers, and data from that app is being streamed into a customer's device and flowing into the lake at some point. In and of itself, this data set is not valuable to sales. But when blended with that same customer's offline purchases that are now being batched into the lake via an FTP ingestion API, the data lake blending process has now found a new relationship between data sets from devices and offline sources that is likely to have value for sales. This is a critical step, as failure to blend the right data means that the data lake engineers have not effectively communicated with their business counterparts and understood the business goals. And that leads to data lakes becoming data swamps. But transformation of that data still needs to occur so that the business can use it. Remember, the data in a lake is raw and unstructured, so it needs to be transformed into a readable and accessible format for the business user to analyze and gain insights from. But upon being published, the strong collaboration between business and lake personnel will be evident when they consume the data. And the business will typically consume it in one of two ways. Number one, an ad hoc approach, where the lake is pushing data sets into a business analyst's choice of database or spreadsheet. Or number two, have the transformation process in this diagram that you see here include a curation step, where the business analyst can use a BI visualization tool like Tableau or Domo or Power BI, just like with the warehouse, and gain the insights as well. Now, there are several different types of data that are coming into the data lake, as with data warehouses, and they can be any type of data. The first and foremost is streaming data. This is becoming more and more popular as devices are streaming in real time. Once they land in the lake holds up the process of getting it to the consumer because of the costly and time-consuming ingestion, blending, and transformation processes. Machine sensor and devices are also streaming their data into data lakes under the same auspices. Number 3 and number 4 you see as external platforms and images and files. These are very traditional unstructured data sets where they come into a data lake and an engineer is probably the only person who's going to know how to stitch that together with other incoming information. But it's all welcome into the data lake, and this is the biggest difference between the data that you see in a lake and what you just saw in a warehouse. Now, we've overlaid the same human icons on the data lake process just like we did with the EDW to show that there are still subject matter experts building APIs for ingestion into the lake, just like with the EDW. But instead of a pre-built schema, once again, which causes a lot of process enforcement, a lake lowers the time spent in that rigid enforcement and simply allows engineers to blend and transform at will. But the caution point here is that when we get to the publish stage where the icon with the stop sign stands, If that lake is storing massive amounts of raw data without having a good sense why the business and IT actually need that data, then there is no management of that data or any mechanism to transfer the source and properly understand the context. The data lake will turn into a swamp. And that's the difference in the cost, time, and risk model. Data lakes may be less expensive to purchase than an EDW, in fact, 5 to 10x less. They're a lot easier to set up quickly and only incremental cost to support depending on the skill sets of your engineers. It takes a far shorter time to gain insights so long as they are effectively communicating with the business, but no long processes or additional personnel or project management routines are needed. The risk here is that stronger alignment is needed between IT and the business. We want to avoid the risk that the lake becomes a swamp with unstructured data that we have no idea where it's going to. And keep in mind, it is still not real time. It's closer to it, but real-time capabilities are simply impossible to enforce with data lakes as they do need to go through some processing. Setting the stage for our suggestion to what the new addition to an enterprise data storage environment should be, let's focus our attention on the two areas of EDW and data lake usage models that cause the most cost, time, and risk to be calculated. Let's take a look at the key differences first and foremost. Once again, structured data versus unstructured data between the EDW and the lake, pre-built rules for rigid data collection on the warehouse side, not rigidly enforced on the lake. The schema on write versus schema on read model was deliberately explained just recently. Setup taking much longer for the EDW, very little setup needed for the data lakes, but the trade-off is that you now have data harder to be assessed on the lake as opposed to a warehouse where it was very easy to act upon. And the last point that we'll recap is that you may potentially miss data that will be valuable in the future from only collecting what's in that schema from the warehouse. It's very rigid, whereas the lake, there's no risk of missing valuable information. All the data is welcome. So let's talk about filling the gap in this case. What are the challenges in each of these technologies? From an EDW's perspective, the work to collect and stage data for readiness is expensive and it's time-consuming endeavor, but the payoff is that when data is ready to be activated or used by the business, the trust inherent in that integrity is less involved. Whereas with the data lake, there is far less work required to get all kinds of big data into storage, but the consequence of such quick collection capabilities is that much more work is required by seasoned professionals to stage it. So we have two diametrically opposed forces here between data collection and data activation. And they have caused enterprises to use both storage platforms, which seems to make sense. But until recently, technology did not exist that could automate, govern, and orchestrate data in real time. And that's what we're going to take a look at in the next couple of slides. Real-time data collection and automation that link a data to a supply chain can execute real-time actions prior to landing in the EDW or the lake. These processes solve the problems because having both the business and IT able to govern and orchestrate big data flows in a single tool will address the shortcomings that both storage platforms are dealing with. These processes and limitations to data processing is what is causing enterprises to fall short of interacting with consumers in real time using cleansed, relevant, and actionable data. So a technology that can leverage real-time collection, real-time action, enterprise governance, and comprehensive orchestration will solve the problem. What steps can we take to set ourselves up for this new way of doing things? Number one, unify these data sources with data destinations in real time. This means that regardless of what device or system is producing the data, the same tool that will process it is the same tool that controls the data collection. Siloing data collection technologies separates the data processing piece from it. And you do not realize the goal of maximum efficiency because data sources continue to be siloed and independent endeavors. So it must be unified. Number two, design an automated data supply chain that incorporates both the process as well as the technology. Currently, with the warehouse and the lake, process and technology are separate. But by incorporating both of them together in a single technology, the concept of building that chain is essentially mapping out the flow from the moment of origination to the moment of activation. The data supply chain, once again, starts from the moment data is produced by an actual user to the moment that the business takes action upon it. Number three, automate enrichment so that they're actionable and lead to insights. Traditionally, we didn't automate enrichments. We had requirements come in from the business, and a data lake personnel would actually build an enrichment and produce some data set. This is a candidate for automation. Recall that data enrichment is merely the result of producing new data that's relevant to all of the silos. The same data produced from a website may take dozens of different forms or enrichments before a marketing department finds it useful. The same can be said for any other department. But in each case, the same original data should just be leveraged once in a single place, rather than each department having to enrich it on their own and realizing cost, time, and risk. Number 4, empower the multiple stakeholders from all the different departments, including IT. Simply put, the data supply chain that is built must be visual, and it must allow the stakeholders to view and orchestrate from a single interface. Number 5, leverage customer data orchestration so that personnel and technology can benefit from a data supply chain from a single data layer. This means that once a single representation of data is agreed upon, every single stakeholder in the business reuses it as a unified blueprint. That blueprint is what governs the enrichments and governs out the activation and integration into the silos. It does it once from a central point and one time only, as opposed to a warehouse and a lake who are logically separated. And last but not least, realize that you're now acting as a true data utility in your organization. This is an important realization because the data supply chain should not have to be constantly revisited and constantly rebuilt. The new architecture is a utility, meaning that businesses can incorporate data as a service for the first time without hiring expensive personnel or hard-to-find subject matter experts. So what does it look like? The final slide, and this is the point that we're coming to. We believe here at Telium that data lakes and data warehouses should continue to play an important role in storing data and acting upon it. In fact, we espouse the belief that warehouses and lakes should have 100% no disruption from the introduction of a universal data hub in the center. If you look at the left-hand side of this document, all of the collecting aspects of collecting data on any device is unified by Telium. It is then standardized into a layer prior to entering the architectural hub that will then enrich via automation, stitch data across different silos to form one unified and constantly changing data set in real time. And at the same time, if you follow the pipes to the south of this diagram, you see the icons for the warehouse and the lake. There is absolutely no disruption from this automation from left to right. Finally, if you stop right here and called it a day, you would have a in-context, real-time customer data set available for you to look at, and that's fantastic. But we don't stop there with this hub. It needs to have a layer of integration around it, because why stop there? Why not integrate in real time with everything you see on the right, whether it's an analytics tool, a digital marketing stack, a call center or CRM, or even a spreadsheet that somebody is waiting to be fueled from in real time.
All right, thanks, Ted. That was a lot of great information. Looks like we have about time for one question, but please answer or ask any questions in the Ask the Question feature, and if we can't get to it today, we'll follow up with you right after the webinar. Okay, so the first question is, why do I need to buy a data supply chain? I've already got integrations from my lake into the website.
That's a great question. The data supply chain, if we remember the slide that is going from left to right, for the first time will integrate data from the moment it originates on any device to the destination where it actually has actionable consumption taken part in it. A lake and a warehouse simply do not do this. Both of those storage technologies, in their own way, in their own efficiencies, will enrich data and present it as information to the business. But to this point, there has been no real-time data supply chain, and that is what's missing from the cost, time, and risk associations.
Great, thanks so much. All right, well, that's all the time we have today. Thank you very much, everyone, for joining us. And Ted, do you want to talk about next steps? Yeah,
a couple more things. From a next steps perspective, we are releasing a new white paper on EDWs and data lakes to summarize everything that we've talked about today, and you'll see that on the website shortly. I'd also like to point out in our adieu that over 800 enterprises trust Telium's top enterprise solution suite. And you can see that here. The Telium Universal Data Hub is the industry's most comprehensive and flexible approach to collect and deliver customer data. You can manage your tags, your APIs, and integrate with over 1,000 vendors to start orchestrating that data supply chain we talked about today from beginning to end. Thank you for joining us, and have a great rest of your day.
Thank you.